Hello and welcome to students. Now today's lectures we are going to discuss the topic chemical kinetics. In this topic now we are going to learn the points first order rate equation. The reaction can said to be first order. It means that the rate of the reactions is directly proportional to the first power of the concentration of the reactant. For examples, these reactants A are converted to products. The rate of first order reactions at any time t, they will be proportional to the concentration of the reactant capital A at time t. Now, small a mole per dm cube be the initial concentration of the reactant, which is starting of the reactions, that is at time t it will be 0, and x mole per dm cube of the reactors can react at time t, and to get the convert into products, and therefore the concentration of the reactants at time t will be A minus x mole per dm cube. At time t, the rate of the reactions will be given by as like the rate is equal to dx by dt is equal to k into A minus x, equation 1. This equation 1 are in the differential equation for the first order reaction. So those equation can we rearrange, then dx upon A minus x is equal to k into dt. Then above equation can integrate between the limits having t is equal to 0, x will be 0. Since no reaction has occurred at time t is equal to t and x is equal to x, then integrate those equations as like the concentrations 0 to x dx upon A minus x is equal to the k into the time 0 to t into dt, equation 2. For those equation integrations can simplify, that is minus ln into A minus x minus in bracket minus ln into A minus 0 bracket complete equal to the k into in bracket small t minus 0. Then after solving those equations, then we get this ln will be common, so ln A upon A minus x equal to k into t, equation 3. Then after by solving those equations or by taking this log, so k is equal to its interchange of those equations, like capital k is equal to this 1 upon t into ln A minus A upon A minus x, equation 4. This equation 4 are the integrated rate equation for the first order reactions. Now, if the initial concentration of the reactant at the starting of the reactions can be denoted by C0, and that at the time t as like a Ct, then those equation can becomes as like the k is equal to 1 upon T into ln C0 by Ct, equation 5. Those equation can be transferred into other exponential form like the k is equal to 1 upon T into log exponential C0 by Ct. Then Ct is equal to C0 into e raised to minus kt. If A minus x1 is the amount of reactant at time t1 and A minus x2 is the reactants at time t2, then we can rewrite as like t1 is equal to 1 upon k ln A upon A minus x1. Similarly, at time t2 is equal to 1 by k ln A upon A minus x2. The difference between these two T2 minus T1 will be as like T2 minus T1 is equal to the 2.303 upon K into log to the base 10 A minus x1 upon A minus x2. Hence, those equations we can calculate the rate of reactions like K. So K is equal to 2.303 by cross multiplications. So T2 minus T1 is here. So 2.303 upon T2 minus T1 into log to the base 10 into A minus x1 upon A minus x2. Now we have going to kinetic characteristics of first order reactions. You know that first order rate equation is K is equal to 1 upon T into log to the base 1 upon T ln A upon A minus x. Now we have see first property unit of first order reaction. From those equations we can calculate the unit of those reactions. So A upon A minus x, this figure they will be a number and therefore K is equal to 2.303 upon T into log into numbers, and hence K is the time, K will be per time or the reciprocal of time, it is the unit. So per second is the first order rate unit or first order reaction unit per second. But since A upon A minus x is the number and therefore value of K will be independent of the initial concentration of the reactant. It is an independent initial concentration of the reactant. Now we have the second characteristics, half-life time for the first order reaction. The half-life or half time of the reactions, that is a T half, is also known as the time for half conversion of reactant into product. Right? It means half of the reactions or half of the reactants convert into product can be defined as the time taken by the reaction is to complete 50% completed and can be calculated using the equation like the K is equal to rate first order rate equation, K is equal to 2.303 upon T into log to the base 10 into A upon A minus x. But such conversions, right? Such a conversion can be half, so half percentage, so 50% conversion. Therefore, x is equal to A by 2. Put this value in this equation, we get T is equal to T half and x is equal to A by 2. So K is equal to 2.303 upon T half into log to the base 10 A upon A minus A by 2. From those calculations, so 2.303 upon T half into log to the base 10. So those calculations, so A by 2, so A upon A by 2. Then 2.303 T half into log to the base 10. So those two, it will be cancelled, are here. So 2 into A twice A. So 1 A and this A cancels. So this is twice, so log 2. Put this log 2 in this here, 0.3010. By calculation, those 2.303 into this 0.3010. So 0.693 upon T half. And therefore, by cross multiplications, so this T half is equal to 0.693 upon K. It is a T half of the first order reaction. Therefore, first order reaction, the time for half reaction, they will be independent for the initial concentration of the reactants, and hence characteristics can be used to determine whether the reaction follows the first order kinetics or not. Next points we have see next characteristics, that is a graphical representation. Those graphs we are shows that this is initial concentrations log of A upon A minus X versus the time, which shows it is straight line graph passing through the origin, and this slope is equal to the rate of the reactions. Consider this is a rate equation of K is equal to 2.303 upon T into log into A upon A minus X. By this cross multiplications, so KT, so K into T upon 2.303 is equal to log of A upon A minus X. So this log of A upon A minus X, write this value, log of A upon A minus X versus the time, then this K upon 2.303 is the slope. So slope is equal to, this is the K. This equation can write in the form of y is equal to mx, and hence the plot of the graph log of A upon A minus X against T will be straight line, and then this straight line passing through the origin, whose the slope, those slope gives the rate constant for the reactions as shown in these figures in the graphs. Now rate of first order rate equation can be written in other forms like this. The Kt upon 2.303 is equal to log to the base 10 A upon A minus X. So this equation can be rewrite as like the log of A minus the log of A minus X, and therefore this log of A minus X is equal to the log of A minus Kt upon 2.303. So from this graph, log of A minus X versus time, they should show such types of intercept. So this intercept is equal to the log A, and therefore slope is equal to minus K upon 2.303, and therefore K is equal to, modify those equations, so K is equal to, that is rate of rate equation is equal to slope into 2.303. This above equation can write in the form of y is equal to mx plus c, and therefore plot of the log of A minus X against time t, they will be also straight line, but it shows the negative slope, and those slope can be used to determine the rate constant of the reactions, that is the K is equal to slope into 2.303. Some examples of the first order reactions are shown is here. The first order reaction can be usually determined by thermal decomposition. The first examples, the nitrous pentoxide can decompose and to give nitrous trioxide plus O2. Other example, phosphorus pentachlorides on decompose to give phosphorus trichloride plus chlorine gas. Similarly, phosphorus pentoxide on decompose by heating to give phosphorus trioxide plus oxygen as a gas. Other examples, isomerization reactions. It means these N-chloroacetanides can decompose and to convert the N-chloroacetanides. Similarly, the radioactive decay obey the first order kinetics as like the radium undergoes alpha decay to use the radon gas. Like this radon gas which on alpha particles and bombard and 2 gives radon. Radioactive decay to radon. So this radium to radon, it means by losing the alpha mass. It is also first order kinetics. Now we have seen this is a very important point to us. Decay constant like a lambda of the radioactive reactions. The decay constant lambda of the radioactive is given by an equations analogous to that for the rate constant of the first order reactions. Like the lambda is equal to 2.303 upon T into log to the base 10 into N0 upon Nt, where this N0 will be number of radioactive atoms present at the start of the decay reactions, that is T will be 0, and Nt will be the number of radioactive atoms present at the time, and therefore this equation can be write in the other exponential form. Therefore this lambda is equal to 2.303 upon T into log to the base 10 into N0 by Nt. Therefore this Nt is equal to N0 raised to minus lambda T, e raised to minus lambda T. Further, half-life radioactive element, they will be given as like T half will be 0.693 upon lambda. Accordingly, the first order rate equations we have seen in last slide. So decay constant for this half-life of radioactive element can be T half is equal to 0.693 upon lambda, or this the decay constant for the first order radioactive element is first order rate equation or decay constant lambda 2.303 upon T log to the base 10 N0 upon Nt. Okay, this is a decay constant for the radioactive first order reaction. Thank you.